So now let's investigate how good or how bad those approximations are from the previous page. So the differential equation that we were looking at was dy dx equals 1 over 2 times the square root of x, and the initial condition was y of 1 equals 1. Now, the exact solution to this differential equation can be found by integrating the right-hand side. So integrate the left-hand side, you get y, and then integrate the right-hand side, you'll know what y is. So let's do that. So we get y equals the antiderivative of 1 over 2 square root of x dx. And now if you want to practice your calculus 1 skills, you can pause the video, but let's do this together otherwise. So I can write this as the integral of 1/2 times x to the power negative 1/2 dx, because square root of x is x to the power 1/2, and then because it shows up in the denominator, it gets a negative exponent here. And so we can use a power rule to calculate this. So this is 1/2 x to the power negative 1/2, add 1 to the exponent, and then divide by that new exponent, and then there's a constant of integration. And so the antiderivative of the right-hand side is square root of x plus c. Now we can figure out what c is from the initial condition. So we know that y of 1 equals 1. And so it follows that if you plug in 1 here, so you get square root of 1 plus c, that must equal 1. And so subtracting 1 from both sides tells us that c equals 0. And so the true solution is y equals square root of x. And that true solution is graphed over here. And the three other things that are graphed here are the solution when n equals 1, right? We found that that approximate solution went through 1, 1 and 5, 3. And then we have the solution when n equals 2 that went through 1, 1 and then 3, 2 and then 5, 2.577, right? And the last thing that was graphed here is when n equals 4. And from the graph here, you can see that the more steps you take, the closer the approximation is to the true solution, y equals square root of x. And here in this table, I've cranked up the number of steps, which is easy to do if you implement this on a computer. And what you can see is that the true solution here on the right, the true solution, the value at 5 here, this point right here, has a y coordinate of square root of 5, which is approximately equal to 2.236068. Now if we use one step to approximate that, we ended up in 3. When we used 2 steps, we ended up at 2.577. So you can do this for 4 steps, 8 steps, 10 steps, 100 steps. and then calculate the error. The error would be how far off from square root of 5 are you? And you see the more steps you take, the smaller your error becomes. And there's another interesting thing going on here. Oops. So if I increase my number of steps, that's basically what I'm doing there is I'm dividing my step size by 10. Right? If I take 10 times as many steps, then the size of each of those steps is only a tenth of the previous one. And what you notice here, hopefully, is that your error goes down from 0.05 roughly to 0.005. So what we see here is that the error also approximately gets divided by 10. And this is actually a feature of the method of Euler, or Euler's method, that roughly when you make your step size 10 times as small, your error becomes 10 times as small. Or if you make your step size 100 times as small, your error becomes 100 times as small. This is not part of the class, but this method is called order H. And if you want to know more about that, I would recommend you take a class like numerical analysis. Okay, now let's do one more example. Consider the initial value problem dy dx equals negative x over y, where y of 0 equals 4. Use Euler's method to approximate the solution at the points 0, 1, 0, 2, 0, 3, 0, 4, 0, 5 using steps of size h equals 0.1. So here we don't have to calculate h. H is given. So we start by listing all xi's. We have x0, x1, x2, x3, x4, and then x5. X0 is our initial value, and so that's 0. X1 is 0.1, x2 is 0.2, x3 is 0.3, x4 is 0.4, and then x5 is 0.5. And you see that each time we change the xi's, we go up by 0.1. So our next step is to calculate the yi's. So we calculate the yi's. The first one is given. We know that y naught is equal to 4. That's from our initial condition. And now y1 equals y naught plus h times f of x naught y naught. Our y naught is 4, our h is 0.1, and then f of x naught, y naught, let's take a look here. We see that f of x comma y is given by negative x over y. So f of x naught, y naught, that's actually f of 0 comma 4. And so this is 4 plus 0.1 times negative 0 over 4. And that just gives us 4 again. So we now see that y1 equals 4. We already had y naught equals 4. Okay, what about y2? y2 is y1 plus h times f of x1 comma y1. y1, we take that from here, that's 4. H doesn't change, that's 0.1. And then we have f of x1. We pick that up here, that's 0.1. And then y1 is 4. So that is 4 plus 0.1 times negative 0.1 over 4. And that will give us 3.9975. So that is our y2 equals 3.9975. Okay, y3 is then equal to y2 plus h times f of x2 comma y2. And that gives us 4. Sorry, no, we're no longer at 4. Right? y2 is now 3.9975 plus 0.1 times f of x2 is 0.2 comma 3.9975. And that is 3.9975 plus 0.1 times negative 0.2 over 3.975. And if you calculate that, we get that. Let's go down here a little bit. So we get that that is equal to 3.9925 roughly. And so let's write that down here. y3 equals 3.9925. And I hope that you see the pattern now. Y4 equals y3 plus h times f of x3 comma y3, and that is equal to 3.9925 plus 0.1, and then plugging in x3, we get negative 0.3 over y3 is 3.9925, and that is approximately equal to 3.9850. Now, depending on how many decimals you need in your final answer, I would keep some extra decimals here for your in-between answer. You can store it in your calculator and use like 12 decimals if you want to. But if your final answer is 3 decimals, I would use at least 4 decimals for your in-between answer so that the round off errors don't accumulate too much, at least. So y4 equals approximately 3.9850. And then finally, y5 equals y4 plus h times f of x4 comma y4, and that's 3.9850 plus 0.1 times negative 0.4 over y4 is 3.9850, and that is approximately equal to 3.9749. So y5 is approximately equal to 3.9749. And so your xi's together with your yi's give you the approximate solution. So it's an approximate solution that goes through those 6 points.